Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. I think we stopped here last time when we were talking about overfitting. So we start to learn noise from data. Instead of learning the general patterns from data, okay, and general trends, we start to learn noise. We start to learn very low-level details that we should not learn. Okay, like the example that we mentioned last time, memorizing the syllabus of the course, okay, before your exam. Or memorizing the examples that we talk about in class or in homeworks. Memorizing it without actually understanding it. Okay? Type. How do we know that we have an overfitting case? When we have very good performance on training, on training, and very bad performance when we test the model on unseen data. Okay? There is a big gap. And usually in machine learning, the performance on the training data is a bit worse than the test data, right? Because it's unseen, right? That's normal. But if there is a big gap, then this is an indication of overfitting, and we'll talk about that inshallah later today. Type. How overfitting can happen in decision trees? If we, I think we discussed that last time probably, if we grow the tree without any depth limitation, without any depth limitation, then every path will probably map to one example. So this is like memorizing or having a specific path for every example. We are not generalizing at all. We are kind of overfitting the tree on the training on every example. Okay, paying attention to every example. Instead of learning general patterns from the entire data, we are learning every single example separately. Okay, so that's the overfitting in decision trees. And we talked also about overfitting in course learning already when we memorize the examples, right? And that the consequence of that is bad grades, of course, in the exam. Any question about overfitting? Type. That we said last time that we have two extremes. Overfitting, when we learn too much, even learning the noise. And on the other extreme, we don't learn almost at all, which is called underfitting. Okay? So imagine an empty decision tree. Doesn't learn anything almost from the data, right? Okay? So in underfitting, we have two cases. When the learning algorithm doesn't learn much from the data for some reason, or we have insufficient data to learn from. In both cases, the performance will be very bad even on the training data. Okay? So that's different from overfitting. Overfitting, the performance will be great, will be optimal, will be perfect on the training data. That's overfitting. Okay? But when the performance will be really bad, even on the training data, and after I train, the performance on training data is really bad, that's underfitting. That's a sign of underfitting. Here is a visual example I think will make things more clear. If we are trying to learn a function, okay? So the dots here, the green dots here are the training data that we have. And we're trying just to approximate a function, to learn a function from this data. Okay? We can do it that way, right? We can try to fit every single example in the data this way. Okay? The outcome, of course, here will be very complex function. This is maybe a very high degree polynomial function, very high degree. Okay? It fits every single point in the data. What could be better than that? What could generalize better? What could be better in this case, in this specific case? What do you think should be the shape of the function? Parabola or maybe quadratic, right? So something like this will be maybe better, right? But this is a case of overfitting, that we try to fit even the noise. Yani maybe the points came like that because of some noise in the measurements of the points. It shouldn't be that way. Okay, type. On the other hand, underfitting, maybe you will learn something very simple that is not even quite fitting good of the training data. Okay, so this is just a line. But maybe better is to learn something like the quadratic function. Still, this is not fitting every example, right? Is that good or bad? It's good in general, right? The bad thing is to do it that way. That's very bad because it doesn't generalize well. And if I gave you now, if I give you this function, if after you learn this function, and then I told you try to expand it, interpolate, and give me the next point. The next point will not be maybe as good as it should be. Okay? Even if I told you if that point belonged to that function or not, it will not generalize. If it didn't see it, because it's actually trying to memorize every single point. It didn't get the general trend or the general pattern from the data. Here, same thing, but on the other direction, on the other extreme. Didn't learn much from the data. Okay? So I hope that this make it clear. Okay, any other questions? So you understand now the difference between underfitting and overfitting? Okay, so the best thing or the better than both is somewhere in between. Okay. Now, we mentioned also last time that that our target when we want to evaluate a model is to get what we call the expected loss. Okay, and we also mentioned that we cannot compute it because it depends on the distribution function, that the probability distribution function that we don't know, right? So today we will focus on how to solve this problem. How can we actually properly evaluate the model? Why do we say properly evaluate here? Because we also said that it's not good to just evaluate the function, the model on the training set, right? Why not? Why don't just we get the accuracy on the training set? Yani we have the training data, right? We train the model, let's say to train the decision tree, and then we take the same training set and test the tree with it to get a measure of how good the model is. Why is that bad? Yeah, so because we can easily get perfect results here, right? If we memorize the data, we can get perfect results. That's not measuring the generalizability of the model. And remember, that was a very important concept, right? We want to make sure that the model generalized to unseen data that it didn't see before. Okay? So our task is to compute the expected loss or expected error. We saw this function before. In case of overfitting, we can, of course, train. So here we want to have a more formal definition of overfitting, okay, in terms of evaluation. We can compute the error, the training error, right? We go through every, let me change this. We go through every training example from 1 to n, compute the loss function for that example, and get the average. Then this will be the training error. We can compute that, right? But that's not what we should evaluate with. We should compute it. We'll talk about why, okay? But that should not be the indication of how good the model is. Okay? What we really want is the true error. The true error is the expected loss that we saw before. We go through every possible example in the world and compute this. And of course, we cannot do that, right? But if we do that, let's just assume for a moment that we do that. Now we have the training error and the true error. That's the real error. True error means the real error. Now, in case of overfitting, what do you think the relationship between these two values? In case of overfitting, the performance on the training will be really almost perfect, right? Type. What should be the performance or the error? So the error here should be almost 0. The true error, what will be the true error? Will it be also almost 0 or much higher? Much higher, right? So that's the definition, or that's the indication of the overfitting. So we say that a specific hypothesis or a function or a model, H here is a model, overfits the training data if the training error is less than the true error. The difference between them, we call it the amount of overfitting, how much overfitting is that we have. Okay, that's the difference. But the main problem here is that we don't know the true error. Okay, that was just hypothetical value. Okay, but we really don't know the true error. Type. What should we do? Here's what we should do. We have the training data, right? We have the training data. All of them are labeled in case of classification, right? We assume that everything is labeled. We will split this set into two sets. So we start with the training set, we'll split it into two sets. One, we'll still call it training set, and the other we call it test set. And we will use the test set only to test the model after training. After training. So we will have here two phases. Phase one is the training phase. We will only use this subset for training. So we'll train the model on this set. Then we test the model on this set. And these two sets are disjoint. What do we mean by disjoint? Completely separate. Okay? There should not be any overlap between them. Between the training set and test set. Okay? So we will set aside the test set. What will we do with this test set? That's phase two. So phase one, training on the training set. After we are done with training, then we do the test of the model on the test set. Now we can compute, or we can get a measure of performance on the test set. Yes. Yes. So that's step 0. Okay. So step 0, split these examples randomly into two sets. Usually it's 80-20%, but it's not a fixed value. Okay. But kind of that. Of course, the test set should be less than the training set. Otherwise, we will be in the position where we don't have sufficient training data, right? So it's kind of 80-20, 75-25, something like that. And we don't look at the test set during training. Okay, and this is what we call a cardinal rule of machine learning. Very important rule in machine learning. What is that rule? Never, ever touch your test data. What do we mean by that? We said that the test set and the training set are completely disjoint, right? That means that while we are training, we are only training on the training set, right? And the training or the learning algorithm should not have access at all to the test set. Otherwise, it will be cheating, right? It will be like training on something that it will be tested on. Like giving you 2 or 3 problems, and I tell you, look, this will be in the exam. Or I don't tell you explicitly. These are very important problems for the exam. Okay? So you memorize even the answers for this, and then you do it in the exam. Did I test you on your understanding now? No. Maybe you got the answers from somebody else, and you just memorize them. So the training set and the test set should be completely disjoint, which means that we should not touch the test data or the test set while we are training the model. Okay? So this is one. Any question about this? Did you understand this? This is a very, very important concept in machine learning. And that's a general concept. It's not specific to a specific model. That's a general concept. Question? Okay. Right. There's another meaning for that, which is related, of course. This also means that you yourself should not touch the test data. Is it just touching like that, Yani? Of course not يعني touching, but you should not look at it even. طيب, we understand that in training, the model should not have access to the test set, right? While we are training. طب why should the designer, him or herself, not look at the, shouldn't look at the test set? Look, seeing it even. The designer might learn something from the data and transfer it to the model, okay? Like, okay, it seems like this feature is very important, okay? Or this feature is not important, let me drop it. Or this feature is very important, let me make maybe a more weight for that, okay? Something like that. Or maybe, yes, the best model, from that data, I think the best model is X, not Y. So you will learn something from the data, right? Yes, in training, the model doesn't see the test set, but you saw it and you transferred it to the model with some bias from looking at the data. Okay, so both are important. That during the training, the learning algorithm doesn't have access at all to the test set, and you yourself should not look at the test set. Actually, the problem here is that the human, of course, is better than the machine. And the human can learn something that will make the model generalize, but by cheating, by looking at the test set, by looking at the exam. And you always think, I think the learning in a course is a very nice mapping, a very nice analogy, or has a very nice analogy with machine learning. Okay, think of it this way. Should you look at the exam before you take the exam? I will not get your I will not get a measure of your learning this way. Okay? We should always the most fair way of evaluating a model is on something that it didn't see before. When you transfer some knowledge or something that you learned from the data to the model, that's not the case now. Okay, is that clear now? This is a very important rule, and that's why it's very, very big sign here. If we have this split, now we can compute the test error, right? Which is error on the test set. So here we are looping over the test examples. We compute the loss function, and we get the average. The loss value, sorry, and we get the average. That's the test error. That's an approximation of the two errors. Yes, that's an approximation of the two errors. Yes. Why are we able to compute this? Do we have the labels for the test set? Do we have the labels? Sure. Why didn't we use it in the training then? Because we have to split it that way to have a proper evaluation, right? Right? So we start with a set of labeled data. We have to split it, training and tests. I think 5 or 10 minutes after, we'll have to split it again. Okay, but we will see. With the test error, now we can have an indication of how good the model is. Let me now show you a visual figure to show you an example of overfitting. Let's assume that for now, forget about this model parameters. Let's assume that this x-axis is the size of the training data. Okay, and I think logically, if as the training data, the size of the training data increases, you should assume that, or should expect that the performance of the model will be better, right? So the y-axis here is the accuracy. Okay, so higher is better. So on training, as we train the data, as we train on more data, we expect that the accuracy will increase, right? So that's the blue curve. The accuracy on training. I'm not talking about testing now, okay? The blue curve is training and then testing on the training. It's like test, it's called test on training. Of course, this is cheating, okay? But kind of cheating, right? Because You might not do well on tests. Okay, but for now, this is expected, right? As we increase the data set, the training data, the accuracy will increase. طيب, what happens if at every point, and let's say that we have 1,000, 2,000, 3,000, 4,000, and so on of the examples, of the training examples. At every point of this, we also have a test set, and we test the performance of that model on the test set. Okay? Yani at every point here on the x-axis, we can compute the training error or the training accuracy, and also the test accuracy. Okay? So here, this is on unseen data to that model, to that specific model. Okay? Is that clear? Fine. Now, if that's the case, that as we train, as we increase the size of the data, the performance on the test set will be better, right? Because we are learning from more data. But at some point, it will drop. So you see here, the drop in accuracy. That means that the model started to be better or worse? Worse. Although it's doing well on the training. This is where overfitting happens. Overfitting means that it will not generalize well. Up to this point, it was. We should expect, of course, that the performance on the test will be a bit lower than the performance on the training. That's normal. But as we increase the data, the model will learn more on training, but will do worse on testing. This is where overfitting happens. Okay? So that's an indication of overfitting. So that means that the model learns much more than it should from the training. That's why it didn't generalize well. The performance dropped, the accuracy dropped, the error increased. Okay? After that point. Okay, so that's an indication of overfitting. When you see something like this, that means that there is overfitting happening. So the best model then that we should keep, or we should have, is at that point probably. That's much better than any model after that. So if you got zero error on training, very good performance on training, and bad performance on testing, then that's an overfitting. طيب. For example, here the resulting, at that point, if we are building a decision tree, so that the decision tree at that point doesn't generalize well. Okay, when we say doesn't generalize well, that means that it doesn't do well on unseen data. Because I can always do well on training. There is a way, right? Memorizing. That's the perfect example. If I can memorize the training data, but I don't know the test, right? I cannot memorize the test because I don't see it. Okay? Fine. So often this means that your model is fitting even noise rather than what it's supposed to do. Type. Formally, we can define overfitting also this way. Let's say that I have two models, H and H prime, like two trees. We built these trees in different way, maybe with different depth. Okay? H and H prime. Let's say that on training, H is better than H prime. Okay? On training, H is better than H prime. On testing, it's the opposite. H prime is better than H. In this case, we call H, we say that H is overfitting because it's doing on training better than it's doing on testing. Let me say it again, okay? Let's say that we have two models, H and H prime. One of them is better on training, which one is it, okay? One of them is better on training, and the other is better on testing. Which one is overfitting? The one that is better in training. Okay? I hope that you understand it now. Okay, that's the definition of overfitting. Any questions? Right. Now we'll talk about model parameters and hyperparameters. What do we mean by that? First, what do we mean by model parameters? Parameters of a model is anything that we use the learning algorithm to learn. There is a learning algorithm, right? What do we give this learning algorithm? Data, training data in general, okay, training data. What's the output? The model, right? And we said that, what do we mean by the model? What do we mean by the model? The model is some set of values or parameters, yes. And we know the values of the parameters using the learning algorithm, right? And using the training data. So we learn the values of the parameters through the learning algorithm from the data, from the training data. So anything that we learn from the training data, from the learning algorithm, is called a parameter. Right, let me give you an example in decision trees. What are the parameters of the decision trees? Think of whatever we learn actually. When we train the decision tree, we learn from the data. What do we learn from the data in decision trees? No. What do we learn from the decision tree? When we train the decision tree, what do we learn? What do we actually learn? Eventually, what is the tree? No, we don't learn the predictions. We don't learn the labels. What do we learn? What are the parameters of decision trees? Raise your hand, please. Mariam? Okay, what is the path? It's a sequence of features or questions about features, right? So we learn what features to ask questions about, and the order of them, and the predictions, if you really mean that, the predictions that we do at the leaves, okay, not the labels in general. I don't know if you meant that or not, but anyway, the decisions we make at the leaves. That's also we learn from the data. So all of these are the parameters of decision tree. We learn that from the data, right? Based on what? Based on the learning algorithm. We have an algorithm, specific algorithm, right? We go through that algorithm. I mean, the algorithm goes through the data to learn these values. We call these parameters. So that's the parameters. We use the data to decide which good values to learn. Okay? So the goal of the learning algorithm actually is to find good values for the parameters that will make the model good, that will make a good model. Okay, is that clear? Usually they are numbers, but in some cases not, like decision trees. Okay, not always, yeah, but usually they are numbers. Any other questions? Okay. So the job of the learning algorithm is to take data and figure out a good set of parameter values. Type. What do we mean then by hyperparameters? These are parameters, but they control other parameters. Like what? We talked about the depth of the tree last time, I think, right? This is a hyperparameter. Do we learn this from the learning algorithm? Does the learning algorithm tells us that's the best depth for this data? No, we don't. Actually, the learning algorithm takes the depth and learn a tree of that depth. So the depth controls the values of the parameters. Then the depth is a hyperparameter for that model. Okay? So hyperparameters are parameters that control other parameters. We cannot easily or naively learn them from the data. And we don't learn them from the learning algorithm. What we learn from the learning algorithm is the values of the parameters. Okay? Type. How do we know the value of the hyperparameter? That's what we will see right away. Type. So we talked about the hyperparameters in decision trees, which is the depth. Type. Now, how can we learn the hyperparameters? How can we learn the best value? Tuning here means the tuning that you see it in the title. Tuning always means getting the best value. How can we learn the best value for the hyperparameters? First, how can we learn the best value for the parameters? From the learning algorithm, right? That's what the learning algorithm is doing, going through the training data and learning the values of the parameters. Right. How can we get the value of the hyperparameter? Can we do that on training? Yani, let's take the decision tree example. I want to know the best depth of the decision tree for a specific problem. I have training data. I will try depth 0. And then, build a tree of depth 0, which is empty. Okay? And then test that tree on the training data to get the estimated accuracy. And then build another tree with depth 1 and get the error on training data. Is that good? We should not test on training, right? That's cheating. So we should not use the test data we should not use the training data to get the best value of the depth, right? Right? Right. Then what should we do? On the testing data, right? Should we do that on testing data? Let me tell you how. Again, I will train tree of depth 1, tree of depth 0, and then get the accuracy for it from on the test set, right? So train on training and testing on testing. Build tree of depth 0, get the accuracy of it. Build tree of depth 1, get the accuracy of it. Build tree of depth 2, get the accuracy for it. Okay? Then at the end, to know the best depth, how can I get it? The one that will give me the best accuracy, right? So looking at the accuracies that I got, let's say that depth 3 is the best. Then the best value for the depth is 3. Is that okay? Is that okay? Did we break it now? Of course. Of course. We use the test data to get the value of the model, to get the value of a hyperparameter for the model. We learned something from the test data. Actually, now we optimize the value to be good for the test set. We broke. It didn't take much time from us to break the rule that I said that it's most important one in machine learning. Maybe 10 minutes, alhamdulillah. Okay? And then we break it. We should not do that, right? You know why now? You understand why? Because we use the test set to learn what is the best value of that hyperparameter for the model. So we learned something from the test set. We should never learn anything from the test set. Never learn anything from the test set. We should only test on the test set eventually. After we learn, learning or training should never be on or using the test set. How can we do it then? We cannot do it on training data. We cannot tune the hyperparameters on training data. We cannot tune the hyperparameters on the testing data. Then what should we do? Let's close this course and then stop here. Of course not. What we should do is to do another split. So we have now the training set and test set, right? We will split the test. We will keep the test set as it is, and then we split the training set into training set. This should be set, not data. Training set and dev set. We call it development set or validation set. Okay? So now we have 3 splits. The same original data, we'll split it into 3 parts. Training, for what? For learning what? The parameters. And dev set for learning the hyperparameters, as you will see now. And the test set to test the model. Right. Still, the 3 are completely disjoint. Yes. So let me show you quickly how we will do it, and then we'll inshallah expand next time. So we'll start on the training data. We'll train a depth 0, 3. And then we compute the accuracy on the dev set. Then change the depth to 1. Compute the accuracy on the diff set. Change to 2. Compute on diff set. Change to 3. Compute on diff set. And so on. Let's say that we will have maximum depth of 4. Now, which value we should have for the depth? How do you know? Why is it 4? We don't know. We have to compare the highest, the one that gave us the highest accuracy on, not on test, on the development set, on the dev set. Because it's unseen to the model, right? Okay, so I can learn from it the best value. Let's say that this is the best accuracy, so the best depth now is 3, because that's the corresponding one, right? Now I take this 3 and test it on the test set to get the accuracy of the model as a whole. So now this is the model. That's the model that I got, and that's its accuracy. Okay, we'll inshallah explain that again next time.